All right, folks, so we are on page 7 of the notes, and the first thing that we are going to do with this problem is figure out the horizontal asymptotes. So as a reminder from yesterday, on the test you'll be given this chart. On the homework, you should be referring to this chart of rules. So don't feel like you have to memorize these. You can always refer back to this chart. So to determine where we have horizontal asymptotes and what their equations will be, we compare the degrees of the top and the bottom. So on page 7, looking at the degrees, is this top heavy, bottom heavy, or same? Same. So I'm going to write same, and again, you don't have to write that on your homework. It's just kind of nice in your notes to have the explanation. So these are same. So we have a horizontal asymptote at, is it x equals or y equals for horizontal? Y equals, at y equals the ratio of the leading coefficients, or 1. So let's go ahead and draw on that asymptote. Now, to find any vertical asymptotes, we need to first find our restrictions on x. So looking at our denominator, we're going to want to factor it, and go ahead and factor the top as well. All right, folks, so factoring the top of this equation, we've got x minus 4 and x plus 1. And on the bottom, we have x plus 4 and x minus 4. So let's start with the restrictions themselves first, and then we will classify them as either vertical asymptotes or holes. So looking at my denominator, what two restrictions do we have on x? X cannot be -4, and it also can't be +4. Those are the two values that would make our denominator equal to 0 and would make the whole fraction undefined. Now, to classify those as a vertical asymptote or a hole, we need to see if either of these restriction factors cancel. Quote unquote cancel, because remember, 0 over 0 does not actually equal 1. We can't actually get rid of the restrictions, but it does give me kind of a fudged value for the whole. So x minus 4 is going to cancel. So that means at 4, at that restricted value, we are going to have a hole. Since the factor that gives me -4 does not cancel, that means this will be a vertical asymptote at that value. So in your slots, we are going to write vertical asymptote at x equals -4, and then a hole at x equals +4. So this is my first time having a hole restriction on the graph. So unlike that kind of first example we did where we were able to easily find that linear equation, this one we are going to use our calculator to estimate the location. So let's just put a note by this one. Use calculator to estimate the location of the hole. Because a vertical asymptote is just through one defined value with a straight line, but that hole value, it's like, well, is it a hole at 4,1? Is it a hole at 4,3? 4 -100? We do not know. So we are going to graph our vertical asymptote at -4. And then we are going to go to our calculator graph a little bit sooner than normal. And we're going to type in this equation. Now remember, folks, when you type this equation in, make sure that you've got y equals x squared minus 3x minus 4 all over x squared minus 16. So revert to the original non-factored equation and make sure you trap the top and the bottom in parentheses. So x squared minus 3x minus 4 divided by x squared minus 16. There it goes. And again, our graph does look like it has a horizontal asymptote right there-ish. It does look like it has a vertical asymptote at -4, but your calculator does not do a good job of showing where the holes are. If I trace 4, we do see that your calculator is like, no, you're not actually defined at that value, so there is a hole there. Have a great Thanksgiving. So we are going to go slightly to the right of that to kind of get an idea of where that restriction is located. So at 4.6 I'm defined, at 3.9.6 I am defined, but right at 4 is where that hole is. So if I were to kind of guess that location on my graph, I would go to 4, there's that x value, and I would say at about 0.6, draw a nice big open dot. So remember, I've got old sleepy eyes, so make your open dots nice and big so I can see them. But that's going to be a key feature that we will eventually sketch through. Now, if you're wondering, well, why aren't we going to draw those swooshes right now? We are going to use our x and y intercepts for some exact points. So let's go ahead and see if we can get some exact points by using our y-intercepts and our x-intercepts. So for the y-intercept, we've got 0 and a number, so we're going to take 0 and we're going to plug it into this equation everywhere we have an x value. So 0 squared y equals.
You don't want to plug it into the factored point.
So that's a good point. I think it's a little bit easier to plug into the standard form for the y-intercept. It doesn't matter. The two forms are the same. But what you're going to find is that factored form is a little bit easier for the x-intercepts and when we have to start thinking about restrictions. So let's go ahead and plug in to our original one. 0 squared minus 3 times 0 minus 4 all over 0 squared minus 16. So 0 squared, 0. Minus 3 times 0, 0. Minus 4, we get a -4 on the top. On the bottom, 0 squared is 0, minus 16 is -16. Why are we not going to leave our answer like this? 1, negative over a negative, not a good deal. Make it positive. What else can I do with 4/16? Simplify it. Take a 4 out of both of those, and we are left with 1/4. So it's a little sloppy here, but our y-intercept as a coordinate is at 0, 1/4. So let's go ahead and plot that point right about here-ish. So 1/4. Now for the x-intercept. Now for the x-intercept, it's easier to use the factored form, but the one thing we need to be careful of with the x-intercept is any restrictions that we have, vertical asymptote or maybe a hole, because it's kind of like having an extraneous solution. It's like, yeah, we solved for this, but it doesn't actually work when we plug it back in. So that's why we start with the vertical asymptotes and the holes. And if you find an x-intercept that is on that line, that means it is not actually an x-intercept. So let's go ahead and plug in 0 for our y value and see what happens when we go to solve it. So we plug in y, 0 for y, or 0 for f of x. And we get 0 equals, now for this one, I have said for x-intercepts, it's a bit easier to use the factored form and to kind of get rid of this possibility of having the whole as an x-intercept, we can actually use the canceled equation. So let's put a note down here that for the y-intercept, it is easier to use standard form. And for the x-intercepts, or the zeros, it is easier to use the factored, canceled form. Ooh, 2 L's or 1 L on canceled? 2 L's? Looks good to me. So x-intercepts plug into the factored, canceled equation. And if you're like, oh no, Mrs. Cairo, what if I actually just put it into the standard form? Or what if I accidentally put it into the full factored form but not canceled? As we showed yesterday with this problem, you can get the same answers. It's just once you get to this point, it's like, oh yeah, it's a quadratic. I'm going to have to factor it. So starting with the factored form saves you a little bit of time. Starting with the canceled factored form saves you a little bit of work of checking it against the restriction. So I'm just trying to show you the easiest way of doing things, but there are still multiple methods you could do. So we've got x plus 1 coming from up here, and x plus 4. So how will we solve this equation for x? Multiply by the denominator. So goodbye to the x plus 4. Denominator times 0 is 0. And we get 0 equals x plus 1. So what does x equal? -1. So -1, 0 for our x-intercept. Is that a restricted value? Nope, it's all good. There's no hole there. There's no asymptote there. So yippee skippy, we got some exact points. So now we can go back to our calculator graph. And we can draw in this swoosh with no exact points. Arrows on both sides, that's an important detail. And then when you curve through these exact points, make sure that the hole is actually an open dot. So I don't actually go continuously through that hole. It is actually a break in my function. So I stop at the hole, and then I keep rising up towards that asymptote. So that would be our graph. So that problem went a lot faster than the ones we did yesterday, but they do take some practice. Every problem's a little bit different as far as the asymptotes and the holes go, and also as far as the factoring is concerned. So folks, any questions on that one before we move on to the next page? All right, turn it. And I think we're going to do these two problems kind of at the same time. I want you to see if you can find the horizontal asymptotes and the restrictions on x, which will give you the vertical asymptotes and any holes for these two functions. See if you can complete those first two steps. And again, feel free to look back at that page that has top heavy, bottom heavy, and same. let's take a look at this first one. Top heavy, bottom heavy, or same as far as the degrees go. Top heavy. And top heavy equations have no horizontal asymptotes. Easy enough. And again, just to reiterate, you don't have to write this on the homework assignment, and you don't have to write anything there. I find it satisfying to draw the line, but you can just leave that box blank. What about on the next one? These have same as far as the degree goes. So we have a horizontal asymptote at y equals 1. And again, folks, I don't really care if you put that HA at part, but writing the full equation that it's y equals 1 is important because that's what shows me it's a horizontal line and not a vertical line. So horizontal line at 1. Let's go ahead and draw that in. Next for the restrictions. Now, looking at this first denominator, what is the one thing that x can't be equal to? -1. To determine if it's a vertical asymptote or a hole, we need to factor and see if that restriction factor will cancel out. So when I factor the top, let's see, product of -8, sum of -7, x minus 8, x plus 1. So does our restriction factor, quote unquote, cancel? It does. And again, can't actually cancel it away, but because of that feature of it, that's what tells me that we will have a hole at -1 instead of a vertical asymptote. So it cancels. So we've got a hole. So hole at x equals -1. And what about vertical asymptotes? There won't be any. So this one will only have a hole. Now, if I go to graph this function to try to figure out where that location of the hole is, x squared in parentheses minus 7x minus 8 divided by x plus 1. It's a line. So interesting. However, it's not just a regular old line, because if I trace that hole value at -1, we see that there is a hole there and our values are not defined there. So let's go ahead and go back to something that we mentioned on page 5. It says, when there's a common factor and we can cancel one of those factors, the function behaves like the simplified expression. Now here, the function behaved like x plus 2, a line with a hole. The one that we just did, it's like, oh great, it behaves like x plus 1 over x plus 4, which is just another rational function that we don't know anything about. But our canceled equation here is something that we are familiar with. So our canceled equation would be f of x equals x minus 8. What type of equation is that? It's linear. It's going to be a line. So yes, I can still verify that on my calculator, but we can be a little bit more exact with the graph and with the location of that hole. So we can start at -8, that's the y-intercept, and we can use our slope to go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. And where do we have a hole? At -1. So folks, if I find -1, It is right here. I better zoom into this. Blech. So I started at the y-intercept of -8 and went up 1 over 1, up 1 over 1, up 1 over 1. So it's going to be a line, but at -1, we are going to have a restricted value. So if I go down 1, back 1, this hole at -1 is going to be the exact location. So by rising and running from the y-intercept, I actually can figure out the exact location of that hole. And it makes our graph a little bit more accurate, which is nice. That's our whole goal with this, is to try to get as many key features on here as possible. Now, if we wanted to check ourselves, we type -1, and it's like, yep, there's a hole there. It's not actually defined. But after you trace, if you move your arrow slightly to the left, we see that at -1.2, I better do this one here. We see that at -1.2, like here-ish, we are about at -9 or down here. So right in there, I'm defined, but anything slightly above it at that exact value of -1 would be our hole or our undefined value. Questions on that one? On your own, see if you can figure out the restrictions on the next one. Factor, look at the denominators, look at if anything cancels to distinguish between a vertical asymptote and a hole. Yep, you can have multiple vertical asymptotes. How are we going to factor the top? GC of... So I know some of you were looking at that going, ooh, I'd really like to cancel something out because they look so similar with the x squareds and the 4s. But when I factor that, can I cross anything off? Unfortunately, no. That means these two restriction factors that give me x cannot be -2 and x cannot be +2, we are stuck with both of them. Neither of them cancel out. So I'm going to have vertical asymptotes at both of those values, which means no holes for this one. Vertical asymptote at x equals -2 and x equals +2. So there's what our graph is looking like so far. So next, let's try to find our y-intercepts and our zeros or our x-intercepts. Is the y-intercept 0 and a number or a number and 0? 0 and a number. And how I remember this is y-intercept means the number that we get is for the y value. Zeros or x-intercept, number for the x part, 0 for the other part of the coordinate. So let's go ahead and find our y-intercept first. And I'm going to show you how we can kind of use the cover-up method with this. If you're like, no, I like what we've been doing with plugging in the zeros, you certainly can do that. but take a look at what happens when we plug in 0 to the standard form. 0 squared is 0. Minus 7 times 0 is 0. What we are left with on the top is negative 8. Then on the bottom, we plug in 0. 0 plus 1 is 1. So my y-intercept is negative 8 over 1. Writing it as a coordinate, 0, negative 8. And I would like you to write these as coordinates just so we can make sure we know the difference between the x-intercept and the y-intercept. So a little less work. Since we're starting to get the hang of these a bit more, you can show a little less work on your homework. So 0, negative 8. Yep, there's the y-intercept, and we already had that on the graph from knowing that our canceled equation was linear. Now for the x-intercepts, or the zeros. So what I'm going to do is use the canceled equation and plug 0 in for the y value. So plugging in 0 for f of x, which is y, we will get 0 equals x minus 8 over 1, or just x minus 8. Multiply through by 1, we get x minus 8. What does it look like our x-intercept is? 8. 8, 0. And as we can see, even though I didn't use my ruler here, there's 8, 0. Another exact point. Now, if we hadn't used the canceled equation, we would have gotten 0 equals x minus 8 times x plus 1. But then it's like, okay, we get x equals 8 and we get x equals negative 1. But when I go to plot negative 1 as an x-intercept, first, does negative 1, 0 jive with this graph? It's like it's not even like connecting to it. I don't even see that as a point on my calculator. So if you don't cancel out that factor, you are going to get a point that is the restricted value or the whole or the asymptote, and it won't make sense with the graph. So this is why, folks, use the cancel equation when you are trying to find those zeros. On your own, I want you to try the next one. Find the zeros, find the y-intercept. So y-intercept, when we plug in 0, 0 squared is 0. Negative 4 times 0 is 0. We get 0. And then on the bottom, we get 0 squared minus 4. What's 0 divided by negative 4? It's 0. So there's my y-intercept at 0, 0. And don't forget that the origin, 0, 0, is not only an x-intercept, it's going to be a y-intercept as well. So when I go to plug in 0 for the y, 0 equals, using the factored form, nothing is canceled in this one, we'll have x times x minus 4 over x plus 2, x minus 2. We multiply through by the denominator. And again, folks, if you want to write out those factors, you can. I am just doing the lazy thing here. So goodbye, denominator. Denominator times 0 is 0. And I get 0 equals x times x minus 4. So x is 0, 0, 0. And x is positive 4, or 4, 0. So on my graph, we've got 0, 0. Let's add 4, 0. And now we have all of our key features mapped out. Now typing this in, make sure you've got parentheses on the top, parentheses on the bottom. Divided by and we can swoosh up to the asymptote, swoosh through that point, swooshing down towards that asymptote. Now, this may be a little bit unsettling as far as the graph goes on this one, because yesterday I said that asymptotes are kind of like the annoying plane, and the graph goes, I'm not touching you, I'm not touching you. But in the middle here, you can see that we are crossing the horizontal asymptote. Horizontal asymptotes are okay to cross because they're not coming from any restrictions. All the horizontal asymptotes really do is they show us what the end behavior is going to do. As we go infinitely to the left, this will level off towards positive 1. And as we go infinitely to the right, that will also level off at positive 1. So because that asymptote isn't a restriction, it is okay that this little middle portion is crossing it. And folks, that concludes our notes over rationals. Yay!